Welcome to linear nth order ODEs. So just a note, so far in this course, we have only seen first and second order equations. So we've only seen first and second order ODEs. Now our goal is to generalize so that we can also solve higher order ODEs. So we are going to focus on linear. So definition. Nth order ODE is said to be linear if it can be written in the form nth derivative of y plus p1 of x times y n minus first derivative of y plus all the way down to plus pn of x times y. And this is equal to an f of x. I apologize, my screen's not updating. So we have the nth order derivative on its own, and then plus a function times each of the lower order derivatives, all equal to f of x. So this is linear if it takes this form. An ODE, so an nth order ODE nth order linear ODE is said to be normal near or at x naught if it can be written in the form of the standard linear nth order ODE, so nth derivative of y plus p sub 1 of x, y n minus first derivative plus all the way down to plus p sub n of x times y equaling f of x, with p1 through pn and f all continuous on open interval AB containing x naught. apologize. I should have said that it's normal on open interval AB instead of normal at x naught. So it's normal on open interval AB if it can be written in the standard linear format where each of those functions of x are all continuous on the open interval AB. So we get a little theorem, which is our standard existence and uniqueness theorem. If our nth order so if an nth order linear ODE is normal on AB, open interval, and x naught is contained in AB, then the IVP with that equation and initial conditions y of 0 equals k naught all the way up through the n minus first derivative of y. Oh, sorry, not at 0, at x naught. So y of x naught is equal to k naught all the way up through the n minus first derivative of y evaluated at x naught is equal to k sub n minus 1. This IVP has a unique solution on the interval AB. So this is essentially the same existence and uniqueness theorem we've seen before. We have our IVP has n initial conditions to match our nth order. And essentially that standard linear form, we just need all of those functions to be continuous. Again, this is standard linear form. The very highest order derivative just has a 1 in front of it. One last standard definition. An nth order linear ODE is said to be homogeneous if it can be written in the form nth derivative of y plus p1 of x times the n minus first derivative of y plus all the way down to plus p sub n of x times y. And this is equal to 0 here. Again, this is our typical definition of homogeneous for linear ODEs. If it does not take this form, otherwise, the ODE is non-homogeneous. So again, we're essentially just generalizing our vocabulary from first and second order linear ODEs to nth order instead of folks specifically sticking with first and second order.